Okay, here we go. We're doing Pollies and Rats, day 5. And so last lesson we talked about complex numbers, right? We can have all different forms of complex numbers. We note that down here with the negative 2i, that's really just 0 minus 2i, right? Our real number is 0. We don't write it that way. That's why we write it negative 2i. So that's considered a complex number. And so today we're going to do something that involves complex numbers and the fundamental theorem of algebra, which the fundamental theorem of algebra guarantees something. So let's just look at things we've done. Let's go ahead and look at this. If we were to find the zeros for this polynomial, right, we'd factor and we get 5 and 2. We've already done that. We get 2 real zeros. And we've done something like this, right? Factoring by grouping. We factored by grouping and we got x equals, looks like 9, and x equals 2, x equals negative 2. We got 3 real zeros. And then with this one, it's very, like, it looks weird, right, when I write it this way, x equals 0, x equals 0, x equals 0. It's a repeated 0. We talked about repeated zeros. But we have it, since it's repeated 3 times, that's technically saying we have 3 zeros. Yeah, so they're same zeros, but there are 3 of them, right? And then down here, okay, so this one we haven't technically done yet. I'm trying to think of what we have covered as I'm making this video. But if we were to set x squared plus 7 equal to 0, right? And we'd subtract 7 from both sides and take the square root, we're going to get plus or minus square root of negative 7, which is plus or minus square root of 7i. So we get 2 imaginary zeros, all right? Or we could say 2 complex zeros. And so now the very last thing that we're going to look at is it's a factoring by grouping. As we factor by grouping, we see that here we get what our x equals 3, and here this x squared plus 7 equals 0, right? One of those things where we're going to get that x squared equals negative 7, so we're going to get 2 imaginary zeros. And so I want us to notice that, look, when our highest power was 2, we had 2 real zeros. When our highest power is 3, we had 3 real zeros. When our highest power is 3, we had 3 zeros that were repeated, but we're going to count that. Highest power of 2, this time we had 2 imaginary zeros, and highest power of 3, we had 1 real plus 2 imaginary, which means 3 imaginary. I'm sorry, 3 zeros. And I want to go back real quick. I want to go back before we do the big reveal of what the fundamental theorem of algebra is. I want to go back to a complex number. I could write 10. That's considered a complex number. So 10 plus 0i is really the complex number part. And so when I see 10, that's actually can be considered a complex number. So when we look at our zeros, even though I said imaginary, oh no, they're gone. Let's reveal them again. Okay, so here, even though we say 2 real zeros, 5 and 2 can also be considered complex numbers, right? Because 5 plus 0i, 2 plus 0i. Same thing. Here's what the fundamental theorem of algebra tells us. It says that basically we're guaranteed a certain amount of, and that is not moving so you can't even see, so we're guaranteed a certain amount of complex zeros. And those complex zeros are going to be equal to the highest exponent, right? So I'm not sure why the words aren't showing up correctly, but the fundamental theorem of algebra says, look, we're guaranteed a certain amount of complex zeros. So complex zeros mean complex numbers. And we saw real numbers can be written as complex. Imaginary numbers can be written as complex. So the highest exponent in our polynomial is going to tell us how many of these complex zeros that we're guaranteed. Now, am I ever going to ask you what's the fundamental theorem of algebra? No. We're just going to know that from here on out, like for this problem, we know when looking at this 4, we're like, we're going to be guaranteed 4 zeros, technically 4 complex zeros. So some of them may be real, some of them may be imaginary, all right? So when we're looking at this, let's go ahead and just jump right into problem number 1. This is the first problem that's on your notes. Let's pick up pretty color. And here we go. So this looks like a quadratic, right? But it's not. It's a quartic, right? The highest power is 4. Now let's go ahead and play the game. Let's pretend. We've done this before. Let's pretend. So we're going to pretend that this is x squared minus 12x minus 13, right? Because that looks a lot like it, and it's a quadratic we can factor, right? We're going to go ahead and use what? X, and a positive 13, and a minus 1. And I'm going to make sure that we are going, and we are. Okay. So we're going to go ahead and take these factors and be like, well, wait a minute. Can't we use these when looking at this? So let's talk about why we are allowed to factor in this way when we have 3 terms. So we have 3 terms, right? And we are allowed to factor this way when it's a quadratic. But believe it or not, when we have 3 terms, even if it's not a quadratic, as long as this number here is even and this number here is half that number, so 2 is half of 4, we can factor this way. So let's go ahead and do it. So when we are, let's get back here. So we're going to go ahead and we're going to pick up the x minus 1 and the x plus 13, but we know, wait a minute, this is x to the first power because half of 2 is 1. Or basically, we're always putting whatever this is, we're putting it there. So basically, here we've got x squared. We need to put a square here and a square there. And voila, if we go ahead and distribute, we're going to get right back to here. So this asks us to find our zeros. So let's get a better color. Not saying that green isn't better, but I need to write smaller too. I'm going to run out of space. So finding zeros, we're going to set our polynomial equal to 0, and we're going to solve. So we have x squared minus 1 equals 0, and we have x squared plus 13 equals 0. So let's go ahead and solve. We've got x squared equals 1, and so we're going to take the square root of both sides, right? Plus or minus. And of course, square root of 1 is just 1. So 2 zeros down and 2 more to go, right? Because we're guaranteed that, I'm checking on my time. I'm not sure why I'm still checking on it, but I am. All right, so let's go back to this one. We're going to go ahead and subtract the 13. When we take the square root of both sides, right, we're going to have that square root of negative 13. And we learned last class, and really you learned it last year, right, that that's the square root of 13 times the square root of negative 1, which is I. So in this case, we knew we were going to have 4 zeros, and 2 of them were real. But once again, I could write 1 as a complex number, and 2 of them were imaginary, which are also. So we have 4 answers that are complex numbers. Then we use complex because think about it. Complex numbers, if we use that term, it encompasses both real and imaginary. So that's a cool thing, right? We've got 2 reals, 2 imaginary, 4 complex roots, 4 complex zeros. We can use 0 or root. All right, pretty cool. If you want to, because we're doing this in class, if you're at home watching it and you want to get another practice with this, go ahead and just pause the video here and do it, and then come on back. All right, so here we go. Check your work. Hopefully you got that right. All right, so here we go. Let's go back to the notes, and let's look at number 2. So with number 2, we've got x squared minus 4x plus 13, and we're like, wait a minute, we cannot factor. All right, so we have a choice. We can either complete the square, or we can, I'm looking around for my calculator. I did not bring it up here. Oh yeah, I did. All right, here we go. So we can either complete the square or quadratic formula. Quadratic formula is easier for students. I prefer completing the square, but here we go. Right, A is 1, B is negative 4, C is 13. Let's go ahead and sing and plug things in. Here we go. So x equals negative b. All right, b is already negative, so we're going to put a 4. Plus or minus square root, cracked a little bit there, b squared minus 4ac all over 2a. All right, so this is what we're going to do because I can already tell that this part is going to be bigger than this part, can't you? So I'm just going to go ahead and put 4 squared. I'm going to put this part right here in my calculator because it doesn't make any sense to do the square root part and get an error domain, right? So what? We're going to have 16 minus 4 times 13. I should know that, but I'm doing the video. So I get negative 36 under here. So that's negative 36. So when we are doing quadratic formula, we got to be really careful that we may get, right, an imaginary number. So we're going to have 4 plus or minus the square root of negative 36 all over 2. Let's go ahead and simplify that. That'll be 4 plus or minus, that'll be 6i, right, over 2. And let's simplify it a little bit more because every single term, right, this term I can divide. Ooh, I meant to get yellow. Okay, so this term can be divided by 2, this term can be divided by 2, this term can be divided by 2. So when we go ahead and do that, we end up with what? 2 plus or minus 3i. So our highest power was 2. We ended up with 2 complex roots or 2 complex zeros. Pretty cool. Fundamental theorem of algebra guarantees that. All right, if we're in class, we're going to do the marker boards. If you're at home and you're watching this video, you can do this problem, pause, and then come back. All right, there you go. Hopefully you got that right. All right, back to notes. Let's do number 3. All right, here we see we have a cubic. We see we can't factor it, even though there's 3 terms, right? Remember our rule. This has to be, well, technically, this doesn't have to be even. If we had a 3 halves here, we could factor using 2 binomials, but nope, that's not what we have. So we're looking at it, and we're kind of stumped, right? What are we going to do? We can't factor it. So we think about our P's and Q's that we've learned, right? And so either 1 works. So let's think about our possible rational zeros. We could pick from plus or minus 1 or plus or minus 7. So we're going to go ahead and use synthetic division and see which one works. I don't know about you, but I'm going to try 1 first. And if 1 doesn't work, you've got to be really careful. So we have an x cubed, and then we're missing an x squared. So we've got to put a 0 in for x squared, and then we've got our 6. So let's hope that 1 works, and if not, we'll try negative 1. Drop the 1, multiply, add, multiply, add. Oh, beautiful, right? So we know, because it says find all the zeros, we've got to stop and go, no matter what, x equals 1 is one of our zeros, okay? Now, what are we going to do with this? We're going to turn this into a quadratic. And if we have to do quadratic formula again, so be it, right? We can do that. So here we go. It's going to be x squared plus x plus 7. And yes, we are going to have to do quadratic formula to find our roots or find our zeros. So here we go. X equals negative b plus or minus square root b squared minus 4ac all over 2a. We didn't have to pick up our calculator, do we? All right, did I make a mistake while I was singing and writing at the same time? Nope, b is right, a is 1, b is 1, c is 7. Okay, so this is going to be what? Negative 1 plus or minus. We're going to have 1 minus 28, so it's going to be square root of negative 27. 27 all over 2. Let's simplify that. We'll have negative 1 plus or minus. We can get that square root of 9 times 3, so 3 root 3, and then, of course, my I all over 2. Nothing else can simplify, so there we go. We ended up with these 2. Obviously, these are 2 numbers, right? 2 complex numbers. And then this one is our third one, a real number. So we ended up with 3 complex roots, 3 complex zeros, right? One of them is real. 2 of them are imaginary or complex. And we were guaranteed that by the fundamental theorem of algebra. All right, once again, if you're at home and you want to try this, go ahead and try it, pause it, and come on back. Okay, so hopefully you got that. We got, looks like 3 zeros, 2 complex, and 1 real. All right, guess what? I don't know. What is behind here? So, oh, okay, conjugate pairs. All right, if we're given a 0, like 4 plus 3i, then 4 minus 3i will also be a 0. So let's go back and see if this was true for us. All right, so here, this is harder to see because it's not in complex number form, but if we were to, rewrite this, it would be negative 1 over 2 plus 3 root 3i over 2. And that would be one of our zeros. And our other zero would be negative 1 over 2 minus 3 root 3i over 2. Maybe easier to see on the other one that we had it. So let's see. Yep. See the 2 plus 3i and the 2 minus 3i? That means if we have a complex root or a complex zero, we're guaranteed that its conjugate is going to also be a complex root or a complex zero. So we did that. So now we're putting some words to it. So when we are given a complex, let's see, what does it say? When we're given a complex zero, so that's a complex number, complex zero, the conjugate of it is also going to be a zero. And we're going to use